Standard warehouses dedicate massive amounts of square footage to empty space. They require wide aisles for human-driven forklifts to navigate, and they store goods on bulk pallets that hold pockets of unused air as inventory depletes. Symbotic eliminates this wasted volume entirely. The company replaces the traditional warehouse floor plan with a dense, 10-level, 3-dimensional steel matrix. The system operates on a principle called atomization. When bulk pallets arrive at the loading dock, the system physically strips them down to their lowest common unit, the individual corrugated case. By managing inventory case by case, the system packs merchandise tightly together without the dead space trapped inside partially empty pallets. Moving these individual cases rapidly requires an entirely new execution layer, a fleet of untethered, autonomous mobile robots. These bots navigate the metal structure right alongside the stored goods, reaching speeds up to 25 miles per hour. Operating hundreds of heavy robots at these velocities inside a dense grid requires new applications of physics, operations research, and algorithmic logistics. Compressing the physical footprint by up to 60% through atomization directly alters the real estate economics of big box retail. It allows companies like Walmart to retrofit their existing distribution centers, rather than spending tens of millions of dollars acquiring land to build massive new facilities. A Symbotic installation fills the vertical volume of a modern distribution center, anchoring to the concrete slab and rising up to the standard 32-foot ceiling limit. To extract items from this structure, the robots use a trayless handling design. Instead of relying on space-consuming plastic bins, the bots extend rigid fingers that slide directly underneath the native corrugated cardboard cases. Maneuvering shifting liquid and dry goods at high speeds across metal decking requires advanced chassis engineering. The robots utilize an independent wishbone suspension system and power casters adapted from the automotive industry to maintain absolute traction control. To move vertically across the 10 storage levels, the bots deploy specialized compliant pinion drives. These drives engage vertical toothed rails embedded in the structure and feature built-in rotational play, allowing the gear teeth to mesh smoothly at velocity without jamming or sharing. Sustaining a swarm of these robots 24/7 demands a rigorous energy architecture. The fleet utilizes 9-volt ultra-fast charging batteries, which recharge in seconds via conductive floor plates as the bots drive over them, eliminating the need for dedicated hours-long charging bays. This specialized hardware provides complete multi-axis kinetic movement. However, deploying hundreds of high-speed agents into a confined structural matrix immediately creates a severe mathematical crisis in traffic management. The primary physical constraints of the system is orchestrating heavy robots operating at speeds of 8.94 meters per second on purposely reduced friction surfaces. In standard warehouse automation, robots use reactive collision avoidance. They detect an obstacle with an onboard sensor and hit the brakes. At 25 miles per hour, this reactive approach fails. A robot's ability to stop is defined by its braking envelope, which is governed by kinetic friction and expands proportional to the square of its velocity. This expanded spatial bubble dictates the absolute minimum safe following distance. A trailing bot must maintain enough space to detect a leading bot's sudden stop, actuate its own brakes, and halt completely without making contact. This dynamic creates a paradox. Pushing the robots to higher speeds decreases the time it takes to deliver a case, but the massive braking envelopes limit the total number of robots that can safely operate in a single aisle. If one robot stops, the trailing robot must brake, sending compounding shockwaves of deceleration through the entire fleet and instantly creating localized gridlock. Managing high-speed warehouse logistics cannot be solved with better mechanical brakes. It is a computational prediction problem that requires a system capable of preventing the robots from stopping in the first place. Coordinating over 400 independent agents through a shared grid is a massive multi-agent pathfinding problem. Multi-agent pathfinding is a computational framework that calculates routes for multiple entities moving to distinct goal locations without colliding. This chart maps the computation time required to find completely conflict-free paths against growing fleet sizes. Seeking an absolutely optimal route for every single robot simultaneously is mathematically intractable. This classification is known as NP-hard, meaning the calculation times explode exponentially past 100 bots. To operate massive fleets in real time, Symbotic utilizes a decoupled hybrid approach, which maintains manageable polynomial scaling. The system divides the computational labor. A centralized warehouse execution system assigns high-level tasks, while decentralized edge computing nodes on the individual robots handle local, priority-based motion planning. To bypass the NP hard bottleneck, the orchestration software relies on an algorithmic shortcut known as windowed math, integrated with rolling horizon collision resolution. Instead of calculating a robot's entire journey from its start to its final destination, the algorithm mathematically reserves continuous corridors of four-dimensional space and time, just 5 to 10 seconds into the future. Before a robot is permitted to accelerate from a standstill, this rolling time-space corridor must be mathematically verified as completely devoid of any intersecting paths from other bots. The algorithm actively penalizes deceleration. It will frequently assign a geographically longer route to a robot if that path guarantees continuous maximum velocity, avoiding intersections where it would have to brake for crossing traffic. By willingly sacrificing absolute mathematical perfection in favor of bounded heuristics, the system processes viable routes in milliseconds. This computational compromise allows the swarm to scale to thousands of bots without suffering systemic deadlocks. Once the robots extract the cases from the horizontal storage matrix, they hand the inventory off to continuous vertical lifts. These lifts act as dynamic sequencers, buffering the downward flow of goods. The continuous vertical lifts deliver the sorted cases directly down to the final mechatronic execution point, the outbound automated palletizing cells. The mathematical challenge governing these arms is the 3D bin packing problem. The 3D bin packing problem is an optimization puzzle that attempts to pack a set of irregular cuboid items into a single container of standard volume as densely as possible. The system thus continuously evaluates dynamic center of gravity physics, strict chemical compatibility laws, and structural crushability thresholds, stacking up to 1,300 unique cases per hour. The software must also adhere to strict retail logic. The pallets are stacked according to specific store planograms, meaning the items are grouped chronologically to match the physical aisle layout of the destination retail store. The central pallet build planner algorithm bypasses the extreme complexity of this task using a flat layer methodology. Instead of solving the entire three-dimensional load as a single equation, the software decouples the math, separating the vertical layer generation from the horizontal footprint distribution. This decoupled pre-planning creates a deterministic roadmap. Because the exact placement of every box is calculated in advance, the two robotic arms can execute overlapping motion profiles inside a single cell without ever colliding. Solving the 3D bin packing problem transforms chaotic inbound freight into perfectly sequenced aisle-ready pallets. When these arrive at the retail store, human associates can immediately restock shelves without manually sorting the merchandise, erasing millions of hours of downstream labor. The sheer velocity and heavy mass involved in these kinetic operations mean engineers cannot risk testing new routing software on the live physical floor. This diagram illustrates Symbotic's hierarchical simulation architecture. The system relies on a continuous, physics-based environment that separates high-level macro-logistics from low-level microphysics and perception. To bridge the gap between simulation and reality, engineers use advanced spatial rendering techniques like neural radiance fields and Gaussian splatting. Neural radiance fields are a deep learning algorithm that reconstructs complex three-dimensional scenes from a set of two-dimensional images. This allows the system to instantly generate photorealistic 3D replicas from simple warehouse scans. This synthetic data trains the computer vision perception algorithms to handle lighting variations and sensor noise. Once validated, the code is containerized and pushed directly to the edge devices on the robots via Kubernetes. When physical anomalies like severely crushed boxes defeat the artificial intelligence, remote teleoperations provide a human failsafe. An operator instantly takes manual control of the bot over a secure black channel network, clearing the jam without requiring a total system shutdown. Combining volumetric atomization, windowed multi-agent pathfinding, and algorithmic palletization yields a massive economic result. The architecture drives down the total cost of ownership for a distribution center by 30 to 40%. This structural cost advantage drove retail giants like Walmart to execute multi-billion-dollar agreements to retrofit dozens of massive regional distribution centers with the technology. By mitigating the mathematical limits of scale, systems like Symbotic convert the distribution center from a static shelter for cardboard boxes into a high-precision, continuous-time computational engine driving modern logistics.